Okay, so let's begin. Just a recap of what we see last time. Okay, so we talked about BGP, right? And we know that BGP version 4, BGP 4, is currently the inter-domain routing protocol standard. Right? So all the AS are communicating for routing, configure the routing path using the BGP protocol. Okay, but we explained that the BGP protocol has a lot of issues. Right? Firstly, you don't know other people's policies, so you don't really know how they choose that path. Right? So some paths may be suboptimal, right? So for a long latency and very slow, but they are choosing that, and you cannot figure out why. And it's totally possible that it's because the other AS misconfigured that. Right? So, and another thing is that even though you don't know why that AS choose that path, but you will see that the AS is choosing that path. Okay, and then you know that your path is not viable because it's not taking the path that you prefer to take after. Okay, so these are the weaknesses of the BGP protocol. Okay, and we then move ahead and say that hey, the policy hiding is really not necessary if you are it's not even possible, practical for the customer provider routing because you probably need your provider to serve you. You need to know your provider's route, right? How you finally reach the destination. So for those vertical routes, right? So you don't need to hide anything. Okay. On the other hand, if you are doing the peering relationship, probably you don't want to forward some information to your peers, right? If you remember, we said in the peering relationship, you have peer 1, peer 2, you have peer 3. Okay, and these two are peering, these two are peering. So when you are communicating with one, you don't need to tell one what like a 3's route is taking. Okay, because only you are peering with 3, not with 1. So the horizontal links, right, the peering links, you can hide information. But for the vertical, right, you don't hide information because you reach there and all the way to here. Right? So your provider, the customer provider link, the other guy will know it anyway. So there's no security that privacy can be protected. Okay, so it's not practical to hide the customer provider routes, but it's practical to hide the private peering relationships. Okay, and actually these are the private, right? So we are talking about the peering, actually including the public, the customer provider routes. Okay, actually 95% of those peering relationships, these links, actually are customer provider links. So basically, almost all of them are customer provider links. Okay, so these are actually, so this actually motivates a new protocol called, hybrid, right? HLP. Okay, so H is a hybrid. Okay, so we have a new protocol that we are discussing here. Hybrid link state, which means link state in the same triangle. That's the hierarchy of the service. Okay, between the service provider and the customer. Okay, and this you are using link state like OSPF, and then you use path vector. Okay, path vector for the horizontal. Okay, so this is what we are talking about here. So this is for the improved BGP protocol. Okay, it's called a HLP. Right? So the reason we don't want to do everything in BGP is because menu configuration is prone to misconfiguration. Right? It can take a very weird route if you misconfigure. Okay, and you cannot disclose the reason, right? Because it's just as the other AS takes that route. You don't know why. Okay, and another thing is that BGP can do a lengthy exploration to find the feasible alternative because it has a list. Right? It will try everything on the list. Okay, we see an example where AS is down, then it will announce different paths to reach the AS until finally it can be sure that the AS is done. Okay, it will withdraw that AS. Right? And there's also, no way to hide any information because if you remember our BGP example earlier, you need to know your next hop AS, every information about it to tell you. Okay, so you see this path to the destination anyway. Okay? So there's not much security privacy. And so small changes in one part of the world will be broadcast, right? Will be announced or advertised to the whole entire world. Okay, so it's globally visible, which is not very desirable. So that's why there's a planning for a new routing framework, right, which is proposed here called the Hlp. Right? So this is based on the idea that, hey, now that your customer provider links are public anyway, right, you cannot hide anything there. Okay, then we just don't hide it, right? So we do it like everyone can see it, just like in OSPF in your intra-AS. Okay. And so an additional semantic visible in the routing protocol would allow, more informed route calculation, right? Because in OSPF, you always find the shortest path. So because you see the entire, you don't hide anything, right? You see the entire information in your triangle, okay, in your hierarchy. So then you can optimize, right? You know how to optimize the route. If one is down, how to find the next shortest path. And to permit better information hiding, because whatever is in your triangle, you don't need to send to the peer. Right? Okay. So we will see the pictorial illustration in the next slide. Okay, so therefore, it's logical to design a routing protocol that uses this parent, the customer provider link. Right? It's like parent-child link. Just don't assume that you don't have control to that, right? You assume you really have you can see that and you can choose that route. So here's an example. Let's say these customers are served by these providers, and these, let's say tier 1 providers. This is tier 2. No, this is tier 1 provider. This is tier 2. Right? So tier 1 is the toughest. Okay. So then tier 2 and then the customer. Okay. Right. So and here's these services are like this. Right? This customer has multi-homing, okay, to 2 tier 1 providers. So, right. And those providers are pairing with each other. So what it can do is, for example, now with this tier 1 provider, all the hierarchy, right, all the customer provider link, we can just treat as a green triangle, and we don't hide anything. We treat this as a public, right? It's just like in your own AS, right? So these information are shared, and this tier 1 provider, and then everyone can choose the best route. Okay? And even some link is down, you can choose the best route, right? Additionally, we have these other two triangles. Okay. Additionally, we have these kind of horizontal links, right? These are the peering links. Okay, the orange ones are the customer provider links. So for the peering links, we can hide information. Right? For example, when this guy is peering, so here, when this guy is pairing with this guy, I don't need to share any information here because these two are not a pair. Okay, if these two are paired, of course they will share information, but at this moment, the whole triangle information, you don't need to share. Right? Okay, so that hides a lot of information there. And there's also, a multi-route hierarchy. Right? So there's a multiple routing hierarchy. So the first is within the hierarchy, within the green triangle. Okay, so there's no need to hide the policy information. Right? You just say, hey, why I choose this route? Because it's short. Okay, everyone knows each other why they are taking it. So it's more transparent. If you find something misconfigured, you immediately know that. Okay, other people's policy, you know this. Okay, so if more information means it's more robust, right? So to make routing decisions, immediately you know, hey, I should take this route if that one is done. Okay, so it's like internally you know everything. Okay? And for the peering relationships, right? So you want to hide information. Basically, you don't need to expose everything internally here to the people. Right? So basically, you're peering with this guy, then you just say, I want you to take the route. Okay. So here, because you think about it internally, it's running a link state protocol, right? Like OSPF. Okay. Here it's running an OSPF internally. Okay? That means it's similar to if you are reaching an AS. Right? So internally, how I deliver this to this destination I don't need to tell the other guy, okay? As long as I reach the destination. So this route information don't really tell outside. Okay? As long as it goes through this tier 1 provider, it will find the route to the destination. Okay? This actually hides a lot of information and significantly reduces the AS path. You think about originally your AS path also included this node, but now you can skip this. Okay? At least skip this node. So the AS path is also becoming shorter. So peering relationship want to hide the policy information, so you don't tell others the path, even how you choose this path. No need to explore low-level path changes. If you have a change here from this to take another route here, you don't need to tell anything to the outside. So the key idea is to use different routing protocols for inside and outside hierarchy. Inside is the orange edges within the triangle. Outside is the gray edges. Okay. So within the orange, parent child, the customer provider links, we use the link state protocol. Okay, so it's a link state is a Dijkstra algorithm. Always find the structure path. Okay, it's kind of similar to this. So OSPF like the OSPF is intra AS. So here we are still doing intra AS, but it's between the customer provider hierarchy. So the nice thing is about we have greater convergence properties, right? So Dijkstra is really convergent very quick. Okay, this is in contrast to path vector or distant vector protocol. Right? We avoid this distant vector protocol, path vector, because they have the poor convergence property, right? Like in BGP, because bad news travels really slow, as we discussed last time. But here, if you have change, I will immediately find the structured path. Okay, the bad news also travels fast. Another thing is that, unfortunately, link state scales very poorly. Right? So because it can only tolerate a moderate number of AS, a moderate number within intra AS and moderate number of routers, interior routers. So the reason is because as we discussed, if you still remember, if you have a graph, so you have a graph, everyone, if they have some link change, it needs to broadcast to everyone else. Okay? So everyone has a snapshot of the graph, the weights. Then they can compute their best passing locally, right? But whenever there's a change, it's broadcast to everyone. Okay? So this is link state. And you think about it, you have a billion node, right? So then you broadcast all the link changes to a billion node. That's not going to scale. Okay, so that's the reason. On the other hand, BGP actually scales much better. It doesn't have this problem because it's a distant vector kind of thing. Right? You only communicate with your neighbors. Right? You don't broadcast information to everyone in your network. And so link state, again, it doesn't hide the policy information. Right? It just finds the best path. Okay, the path vector information. Right? So you don't need to tell others why I took this path to the destination. Okay, so this is security is better. So we can see that the pros and cons. So our solution is to do this, right? Inside the hierarchy, we do the customer provider links, okay? And in the peering links, we do the link state protocol. Okay? In the peering links, we do the BGP kind of, okay? So outside, we do the path vector. Okay? Here, because these protocols contains additional information rather than just the path one. We are talking about the key information, but these have additional protocol information. Okay? So we are now using the more high-level categorical terms like link state and path vector rather than the specific protocol. Okay? So in the triangle, we want to use the link state. In the horizontal line, we want to use the path vector. So it's a hybrid link state and the path vector. So this gives you Hlp. This is how the new protocol name comes about. Okay. So here's here's again how the name comes about. It's a hybrid HL link state P path. Okay. So from now on, we will just mention Hlp. So you will please don't get confused why it's Hlp. We are just talking about this thing. Right. So here you can see that we have a tier 1 service provider. Right. So they generate 3 hierarchies. Okay. And this one is shared by two of them. Okay, and these are all the downstream customers. Okay, and then they have also parent links like this. Right? These two tier 2 provider up here, and these two peer, these two and these two up here. Okay. So what we'll do is within the triangle, each triangle will run the link state, but everyone can see everything else in the triangle. Okay. And then horizontally, we will run the pass factor. This is like OSPF inside. The pass factor is like regular BGP. Yeah, something like this. So here's a Hlp protocol. Okay, is actually proposed, in this paper. So I'm not sure whether you're familiar with networking domain. Right? So SIGCOMM is like the best conference in computer science. In computer science, we look at more on computer science conference than journal. Okay? Because computer science is moving so fast. If you have a journal, it takes 2 years to publish. It's totally outdated. Okay? So usually you have a conference paper, and then you extend to a journal, right, with a more complete knowledge. And everyone is just reading conference paper. Okay? So SIGCOMM is the best conference in network domain, and the others are like Infocom, etc. Right? So, and there's also mobility domain for like Mobicom, Globicom, etc. Right? So, but SIGCOMM is really top. Okay, around the world, every year it's around 30 papers are accepted. Okay, so it's around the level of companies like OSDI, right, where TensorFlow, like MapReduce, publish. Okay, but it's in the network field. And another more system-related, this is a protocol, right? So this is a very network. Okay, another more system-related venue that is also very top called NSDI. Okay, you later see these things, it's super top. Okay, and in this paper, they publish, I don't recall which year, they published this concept called Hlp, but to improve the BGP. Right? It's called the next generation BGP because they studied this problem, right? And then find, hey, we should really do a hybrid scheme. Okay, so the hybrid scheme, as we iterated again and again. So within the customer provide links, we use a link state tree. Okay, the reason is because of good convergence, we don't have the bad news convergence slow issue. Okay, and we have more information, right? So we can compute the alternate route really fast. Okay, use this. Remember our distance vector protocol, right? The Hrp. Okay, it takes forever, almost forever, to propagate the bad news if a link is down or it's becoming very time consuming. And it also explicitly represents the backup links for the multi-home because you have the entire tree. So here we think about it, entire tree. You have the entire tree, then you of course you have the whole snapshot. You know which of the backup links you should take. You don't need to list everything, in your AS. This is a way space more efficient, right? So because you have the snapshot, you know which one is the next shorter path after this pass is done. You don't have to keep the combinatorially number, as this is a permutation, all possible potential paths things. Okay, and the default policy is also simple robust, right? Because you can just use the shortest path. And so a lot of times you don't care about which AS you pass. In that case, you don't even configure it, right? So then it will run OSPF kind of like a Dijkstra algorithm, right? And if you don't want to go through this, and you probably find the second short path that doesn't go through this, right? So that's possible. But the default one, if you don't configure anything, it will run things just like a Dijkstra algorithm. And there's also improved the default security, right? Because you need to be the tier 1, okay, the top level service provider to do much damage. Right? So because if you are tier 2, your damage is just here, but tier 1, your damage is the entire thing. Okay? So the security is improved. Any question? Okay, so if this is fine, let's continue. So here we are Hlp, we have the link state part. Okay, we also have the path vector. The P is path vector. Right? So this is if you are between the customer and the provider trees, right? So you have the peer links, and we are using the path vector. Right? Path vector. Okay. But we are using so-called fragmented path vector. Right? Because whatever you pass, so you go here, but you have some internal pass, you don't care about it. Then you peer again, and what's internal in the triangle, you don't care. And finally, you reach the destination. And that's called a fragment because, this segment is in your AS path, this I don't care. Okay. This is in your AS path, this internally, I don't care. This is in your AS path, I don't care. Okay. So that gets a fragment. The straightforward benefit of this solution is that you can see your paths become shorter. Right? So that's very important because we know that if there's a lot of announcement, it's really because of the permutation of the path. Right? If you permute 5 links, it's going to be way less than if you permute 10 links for sure. Right? So that's much better. Right? So the number of links is significantly decreased. Okay, and this also therefore reduces the path exploration space because within the triangle, for example, you use it for policy. Of course, you will take the short path to reach. Right? So you don't need to permute anything. Maybe there are 3 hops. Right? If you do the permutations, there are 6 possibilities. Right? You don't need to handle this. Okay? You don't need to go the complicated permutation. Right? And so another benefit is that it degrades. The performance can degrade, right? So, but it degrades gracefully, right, from the link state towards path vector if the ISP use non-default policy, right? So if you look at this triangle, my shortest path is from here to here and go up, right? But I don't want to use this AS in the path. Right? I can use this. Okay? Right? It's now the second short path which could not pass through this guy, right? So in the worst case, you say, hey, my policy, I don't want to share everyone else's policy. And then you list everything. And this is the worst case. The worst case is just BGP. Right? The ideal case, you don't even need to keep this here because it's a default policy. It's a short path. Any questions? Okay, let's continue. So another thing that if you establish it, so here's let's take a look at why these protocols are interesting. Right? So here I think we have 2 animations to show the process. What is going out of your triangle? Right? So this is like one triangle. This is like the second triangle. Okay. What is not going out of your triangle? Okay. Let's take a look. So assume we have a new link. This is a new link, by the way, CE. Okay. This new link is established. Right. And originally, because we are still considered cost using number of AS in the past. Okay? Internally within the AS, we don't care. So if you look at here, originally, if we go out, let's say we don't have this link. If you want to send out something, it has to go through 3 hops. Then what do you do? Okay. But if you have a new link like that, like CE, then you only 2 hops will go. Okay. So that's much better. So now you have this link because we are internally running link state protocol. Right? We need to tell everyone, hey, now I have a CE and the cost of 1. Right? Originally infinity. Right? There's no. Okay. And this information will be public to everyone. Okay. Broadcast. When reaching A should have this path tree, right? So it knows, and now I should go ACE, right? If someone asks me to do this instead of ADFE, okay? Then when A is sent out, I don't really care about which path you take, whether ADFE or ACE. I just say, hey, I can deliver things to E, right? Okay? And the cost 2, because now I have a new path. Right? It's reach A, it knows this path, so it will say cost 2. It hides all the information inside this triangle. Okay. And now when B reaches, right, so B will say, hey, now B goes to A and then A can deliver to B. Okay. The cost is 3 because you have another gray link here. Okay. And then when it goes to G, right, also broadcast it. Internally, you don't really need so this is called a fragment path vector. Right? The fragment means you only need the border gate, the tier 1, right? These gray links end nodes. Okay, you really all the source of destination. Okay, your E should be there, right? So you reach E instead of reach other node. Okay, but otherwise it's just those nodes that connect by the gray links, not the orange. Okay? So the BA, right? So BAE. Okay, but even in reach G, GB, this edge is not including the fragment path. Okay, the cost should be incremented because now internally you have another ASF. Okay, And similarly, if you reach here, it cost becomes 4 because you have another GH. Any questions here? Right, so I think this should be fine. Right, so now let's think about a path withdrawal. Right, so let's assume this link is gone. Right, so now this AS will detect what? Will detect, hey, CE is no longer reachable. It will send everyone, hey, now it's infinity. Right, so let's assume the broadcast is here. Right, and in the meanwhile, C, this is also adjacent to C. Right, C will also find, hey, there's no heartbeat to E. Right, so it's infinity. Okay, so it will go all the way to. And so C and E will both broadcast this information of cost infinity for the edge CE. And then the next hop C reach A, E reach F, right? Then both of them will notify the rest, which is D. Okay. Thank you. Let's take a look at what do we come out, right? So this time it come out because this link 2 is no longer viable, right? The short path is this one. So it will tell, hey, A to E is cost is 3 instead of 2. Right? But you don't expose the DEF, those information. Right? That's how you get a fragmented password. Okay. And now everything is pretty similar to the previous. Except that now 3 plus 1 is 4, right? And 4 plus 1 is 5. Okay. So the cost is increased by 1. Right? 1 more AS. But you can see that even we have 5 AS in the past, right? We only show 3, okay, because of the fragment part. So for those gray links, we still need to do different kind of permutation, but because this internally it's determined, right? So we don't need to involve them into the permutation, okay? So that's actually reduce the path length, the link length in the path vector, and thus improve the performance. And so there's also benefits from the isolation and the information hiding perspective, right? Because actually, if you look at the diagram here, if you look at the number of links, most of the links are actually orange links between customer and the provider. Okay, the peering relationships are not so many. Okay? So this is reasonable, right? Because as long as your service provider have a contract, then they agreement, right? Then they peer. But a lot of the customers, they don't peer with each other, right? Especially the end users. Okay, so because of this reason, because this reason, most of the information are within the customer provider tree. Right? So then you expose very small amount of information that need to run BGP from outside. Okay, you also don't need to convey all changes into FPV, right? So the path vector, because the path vector don't care about whatever in the triangle, in the hierarchy. Okay, it only care about what is on the gradings, not the oriented path, right? So local changes are not too critical, right? So if you have some change, one AS in your triangle is down, that's fine. We'll take another path, just like the 2 animation we showed earlier. As the CE edge is down, it's fine. Outside the world, you don't see which route it's taking. Right? So you go from ACE to ADF, but people don't know DNF. Right? You can see here you don't see DNF. Okay? So that's a lot more secure. Right? So only large scale changes need to be pushed to the password. Okay, and it also significantly reduces the global routing table. Right? So the global routing table trend, right? Because of the gray links are much less. Okay. Right. So there are some exceptions, though. Right? So, for example, not all policies right conform strictly to the hierarchy. Okay. Some of the policies that we implement may not be able to run with link state. Okay? It has to rely on the BGP protocol. So, for example, if you have a exception, right, like a policy, and some prefer the customer exception, right? So maybe I don't want to serve that going through that AS, etc. Right? So in that case, you still need the path information. Right? If you don't have the path information, right? So you won't know, hey, there's an AS here. Right? So for example, BGH, okay? But I don't want to get my packet from, for example, E through G, right? If that's the case, then you still need additional information. You cannot just do the link state. Okay? So these are the exceptions, right? If you don't know there's a there's a ASG in the middle, then how can you bypass it? Right? Let me see this. Let me see this. Okay. And in that case, you will put that path into the fragmented path vector. Right? You need to expose G to the path vector. You cannot just hide it like in this. And this is fortunately very rare, right? So you can see less than even 5%, 0.5% in most cases. Apparently less than 1%. Okay, so this is a provider link, this is provider peering, this is a peer provider. So, okay, so but from every categories, you can see this export policy exception is very, very limited in 2000. I think this is 2003, very early. And another thing is that when we have the protocol, right? So when the route changes because of some link is down, or some link becomes slower, or some link become newly established or faster, right? So then this information will start to propagate, right? And the original BGP protocol, right? It's not good. Okay, the worst case, you can search for all possible paths, right? So the permutation, right? That's crazy. Okay, and using Hlp, right? So your convergence time becomes much less. Okay? It becomes n times kd. So n is how many AS you have in the network. So if you look at here, all the blue node, right? That's AS. Okay. And another concept is let me see here, the KD. Okay. So KD is the number of peering links on the path, right? So if you come back to the peering links here, only 3. 1, 2, 3. Okay. So that's way smaller. Okay. So you may ask the question why the cost like this, right? So because you think about it, right? So you at most pass the permutation based along this path, right? So there are most n passes. Within there, you don't need to pass any information. Okay. Let me find this page. So this is very, very small. Okay. Moreover, actually, people find that when you do the internet routing, okay, this number of peering links that you passed, most of them most have one peering links, right? So 90% has one peering links or purely customer provided links. Okay. In that case, it's n. Just convergence time is just how many nodes you have on the path. Okay. And the 99% is actually less than 2. You may pass through 2 peering links, but that's very rare. Okay. And all internet routes, right? So whatever you do the routing, just will be no path passing through 4 pass through the 4 peering links. Okay? So the peering links are like that. So you at most do something like, for example, let's say you want to route here, and then you route here, right? And then you route maybe here, right? You pass this thing, so route here. Okay, there are 2. Okay, right? At most this kind of gray links can happen for 4. Okay, no more than 4. That's a guarantee. Okay. So then you actually your convergence time is super fast because the k factor is small. Any questions? As long as you get the high level, that should be fine. Okay. We will just test your concept. We will not test you the low levels. So what's the advantage of Hlp? Apparently, this is because the stability is improved because your path vector, right? So it's fragmented path vector, which is much smaller, right? And it also hides a lot of information of what is inside the hierarchy, right, in your kernel. Okay. But the second benefit is the convergence is fast, right? Because link state converge fast. The only case that, if you still remember what we teach when we talk about link state and distance vector, is that only distance vector has this count to infinity problem, right? Where if you have a link that becomes slower, right, and it will iterate until you by 1 each time until you reach the final longest, the weight of the edge. Okay, but the path is reflecting the real cost. Okay, otherwise it will slowly go there. Right? So that's the come to infinity problem, right? So link state doesn't have this problem. It dictates very clean. Okay, it's each time you choose the next structured path to finalize it and update its that node's neighbors. Okay. So link state converges faster, right? So and the frequent path vector FPV converges faster than path vector, right? Because you have fewer alternatives. Okay, within the triangle, it's a deterministic path, and you don't need to care about it actually. Right? And security is also, improved. Okay. So there's also robustness. Right? So because it will be difficult for you to misconfigure, right? So the default one will be in the hierarchy will be shortest path. Right? So a lot of time you don't even need to configure. It will take the default. Okay. All right. So that's all for this slide. Any question? If not, let's take attendance. So we'll take a quick attendance and then we will move on to the next one. Okay. Okay, let's start from our fifth student. Okay, Stephen. Stephen.
Here.
2, 3, 4, 5. Alex. Alex, are you here? Alex? No. 1, 2.
Wait, Alex, who? Can't see your screen right now.
Oh
I don't
no.
know why.
No, it's not. 1, 2, 3, 4, 5. Cass? 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 No.
Check the chat. She's here.
Oh. Thank you. I didn't see that. Thank you. Yeah. 1, 2, 3, 4, 5. Corey? Corey? Corey here? No. 1, 2, 3, 4, 5. Daija? 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 Juran? No. 1, 2, 3, 4, 5. Trina? Trina?
I'm here.
Okay. 1, 2, 3, 4, 5. Andrew? 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 No. I think Alex Hamilton, I didn't call you. I think another Alex. Let me double check. Not you. Okay. Well, Daniel? I think Daniel.
Here.
Yeah, I
Daniel.
remember. Okay, good. 1, 2, 3, 4. Miller?
I'm here.
Okay. 1, 2, 3, 4. I didn't count. 1, 2, 3, 4. Brooklyn?
I'm here.
Okay. 1, 2, 3. Bryna?
I'm here.
Okay, good. Let's go to the next list. Nancy? Nancy?
Yes, sir, I'm here.
Okay. 1, 2, 3. Matthew?
I'm here.
1, 2, 3, 4. Hanchao Lee?
I'm here.
Okay. 1, 2, 3, 4. Rohan?
Yes, sir.
Okay. 1, 2, 3. Joshua?
I'm here.
Okay.
I'm here.
Got it. 1, 2. Okay. That's all for the attendance. Yeah. Go to the next next slide. We'll check the beginning and then I see a chat. Just one. Okay, so now we are moving to the transport layer. So far, we talked about routing, right? It's in the network layer. Okay. So we finished these 3 layers. Now we are in the transport layer. So what's the purpose of this transport layer? Okay, because above transport layer we have the application layer, right? So it's really demultiplexing the data stream because you have so many applications. You just think about how many apps you have on your phone, right? On your smartphone. Each app will all through the same physical device. Right? So you need to say, hey, this communication is to this app, that communication to that app. Right? So if you are using WhatsApp to communicate, right? You don't want WhatsApp's information to send to your email app. Okay. And so this is called demultiplexing the data stream. Okay. And there's also optional functions, which actually most of them are in TCP protocol. Right? We also have a UDP in the transport layer, which we don't have most of them. Okay. The first is creating a long-lived connection. Right? So why this is important? Because it's unlike your phone, right? Phone call, right? You have a circuit switch. Right? Here, internet, we have a packet switch. Okay. Basically, you from the lower layer, it's just a small packet. Okay. Right? So how do you create a reliable connection between 2 parties? Right? And you can keep sending stuff. Okay. Right. And including, for example, you are doing online shopping, you have a session. Right? So this is actually above the transport layer. Right? You have a session that you log in and it keeps it. And another thing is how can we guarantee the reliable in-order packet delivery? Right? So this is very important because a lot of the data are sequences. Right? So if you reverse the order, it could be totally wrong. Just think about, let's say, a credit card number, etc. Right? So that should be a order. Okay, and you should have some error detection mechanism just in case there's an error flipped and you do a transaction. Right? Maybe $10 become $1 million, then you don't want. It's just a kidding. Right? So, but I mean, you do want to have error detection mechanism in a lot of the cases. Right? A lot of them are not necessary. Let's say when you are watching YouTube videos, potentially that will be done by UDP. Right? Because hey, then an error, pixel have a wrong color, it's fine. Okay, and if it's not reliable, it's fine. I use that frame. I can continue watching it. Okay? But in a lot of other applications, right, we need TCP. Okay? We will see that later. And we also have the flow control and the congestion control. Right? So you will see this a lot in the TCP protocol. Right? So we have 2 controls. Right? It's called a flow control. Another is congestion control. So what are the difference? Flow control is really caring only about the destination. Right? If your destination can only receive things in that speed. Right? So if you're, let's say you type, for example, you can receive maybe how many words per second. Right? But other people are speaking super fast. Right? Then that's not good because you lose almost all information. And then because it's a reliable transmission, then you need to read. You speak those things again and again. Right? So why not just let the sender speak slower? Okay. So when we talk about flow control, the concept is you have a sender, you go through something through the router, and then go to the receiver. Okay. If the receiver is slow, you have to speak slowly. Okay, then receiver can get things without have to do. You don't have to talk to him again. So you just slow your pace. Okay. Congestion control is a different concept, right? So congestion control say, hey, even though you can receive so fast and you can talk so fast, right? But because it's a complicated routing network, right? So there may be some other people also sending stuff, right? And this will maybe even not to you, to somebody else, but you are sharing this link. And this guy is using a lot of the bandwidth, right? So here this is the bottleneck link, right? So you cannot send that fast through this link. Okay? So this path is not, the bottleneck is not on the sender receiver side, but there's congestion happening. Okay? So this time then you need the congestion control. So these, both of them are presented in TCP, right? So what are the key challenges? So the key challenge is how you detect and respond to congestion. How do you find, hey, now I cannot send so fast. Right? Apparently, if you lose a packet, right? So you send too fast and the receiver cannot get it, cannot acknowledge your packet, then you will find it. But we will see more details. Okay? Another is how do you balancing the fairness against high utilization, right? So fairness means, hey, if I have so many people sending through that common links, okay? But ideally, they should each at this link use 1/3 of the bandwidth, right? Okay? Right. You don't want someone to use maybe 90% of bandwidth. Other people have no bandwidth to send stuff through. Okay? Right. So this is called fairness. TCP actually guarantees this fairness. Right. But it will take steps to do the back off and gradually reach that balance. Okay. But again, you want a high utilization, right? So you don't want to waste. When you do back off, you suddenly reduce the bandwidth. Actually, you don't want to occupy 90%. Right? You find, hey, there's some packet drop, you back up. Right? And then actually you're wasting some of the bandwidth if everyone is back up. Right? So you want to minimize the time that the utilization is wasted. Right? You want to, when it's possible, you want to increase your sending speed until you hit the, hit the wall. That's packet loss. We will see those details later in the slide and the next. Okay. And so firstly, let's look at the concept for multiplexing, right? So multiplexing is on the sender side. So we have the same network interface card and finally go to the same path through the routes, okay? Right. But unfortunately, because the internet is datagram network, right? There's no circuit, no secure connection. Right? So you have so many different applications, right? So one thing is you need to multiplex all those data informations into, kind of one stream, and then you can send out. Okay, so this is multiplexing, and on the receiver side, you have the demultiplexing. So basically, here's an example. Okay, this app is sending email to here, and this app is also sending email to your mail server. Okay, you need to be able to demultiplex. Okay, although for your router, these different traffics are all the same for them. That's just small packets. But as a destination, after transport layer, you should deliver to different applications. Okay? You don't want to have something like your Chrome traffic finally go to your mail, and your mail traffic go to your Chrome. So that will make the application crash if they don't recognize this message. Okay? They cannot pass it properly within that program. Okay? All right, I think there's only 1 minute left, so I will potentially just stop here, and we will continue next time because it will take some time to finish each slide. Okay, any question? I will be here for 1 minute just to get your questions. Okay, I have one message in the chat. Let me see. Okay, I don't see a question. Thank you, and I will see you guys on Friday then. Okay. Have a nice day.